All right, so the first set of problems just gets at the idea that you have a function and we want to evaluate it at these x coordinates. So if you notice, this is usually f of x. When we replace that x with a -1, it's just telling us we're going to replace all these x's over there with a -1. So wherever you have a -1, you're going to substitute that in. Whatever this evaluates to be is going to be your answer. So it's a little test of some order of operations. We do exponents first. A -1 squared is a 1. -2 times a -1 would be a +2, and then plus that 1. So what we really have here is a 3 plus a 2 plus a 1. Add those together, and we get 6. So f of -1 is going to be a 6. What that then really means is that the point -1, if we wrote this as a point, has an x-coordinate of -1 and a y-coordinate of 6. All right. If we go to this next one, you're going to let your x's become a 0 now, since f of 0. So f of 0 would equal 3 times 0 squared minus 2 times 0 plus a 1. Again, I'm just using this function to substitute those things in. Zeros typically are pretty nice for a lot of reasons. This would just all zero out. This would all zero out, but we do still have that little plus 1 in the back. So f of 0 would be a 1. If we do f of 2, same thing. You're going to take that original function of 3x squared minus 2x plus a 1. Substitute in a 2 wherever you have an x. And then evaluate that. So this would be 3 times 4 minus 4 plus a 1, which would then give you 12 minus 4 plus a 1. Combine all those guys, should get a 9. F, for whatever reason, I'm not sure what happened here, because I don't even have the letter D, but f of 2 would be a 9 as well. It's obviously the same problem here. The rest of these, or at least the next handful, are just solving equations. Something we did, again, at the beginning of the year is a little refresher what you would have done in Math 1. So with these, I would think most people would probably go about this via distributing. So we'll distribute that 7 to 6, so 42. And then the 7 and the -8 would make 56. Then we just go through whatever steps we need to get the x by itself. So in this instance, you're going to add 56 to both sides so that those would cancel. You now get 42x. And then we add those up. So we would do 196 plus 56 should give us 252. All right, from here to get the x by itself, you divide by 42. And when we do that, get a nice value of 6. 7. Again, I'm going to kind of go about this with distributing, even though there are some other ways to go about this, but I think that's probably what people would see first and probably would go through. So we'll distribute that 3. We'll subtract 3 from both sides so that we get 18 on the left equals 3x. Divide by 3, and your x should be a 6. We then did any couple equations or earlier in the year where we had x's on both sides. Our goal, we would want to make sure that all of these x terms are on the same side. So now we actually have x on both sides of the equal signs. So we want to move one of them. I'm going to move this x by subtracting it. By moving it, it just means we're going to get rid of it from the right-hand side. By subtracting that, that's going to be gone, leaving us with just a 9 on the right-hand side. If we then do that to the right-hand side, we have to do the same thing to the left-hand side. So if I did 8x minus a 1x, that leaves me with 7x's on the left. I still have the -5 as well. Continue to solve. We now add 5 to both sides. So 7x is going to be a 14. Divide by 7, and then x should be a 2. All right, 5, same thing. We'll distribute. 1/2 times x is just 1/2 x. 1/2 times 4 is the same as saying 1/2 of 4, which is 2. Continue solving. I'm going to add 2 to both sides. These will cancel, and 1/2 x would equal 12. Then up to you. People that I've asked today, yesterday, how we would do these. A lot of you were telling me to divide by 1/2, and that's okay. My guess is most of us would probably need to rely on a calculator to enter that. You would definitely need to kind of want to use that fraction key. So if I gave you 12 and then you wanted to divide by 1/2, if we do the alpha y equals, that would pull up the fraction bar. Divide by 1/2. Notice how that is a 24, so that's going to end up being our answer. That's what most people that have been getting this problem and ask me about it do. But what we could also do is if we're multiplying by a 1/2, I want to get rid of that fraction. I could just multiply by 2. Because 2 times 1/2 is 1. You'd have to do the same thing to the other side, which is multiply. So either way, when we multiply both sides by 2, you're going to get that x value to be 24. All right, number 6. Subtract x from both sides so that we get -1 would equal 2x minus a 5. Continue to solve for that x. Now we'll move the 5 out of there by adding it so that this will cancel. So we get 4 is equal to 2x. Divide by 2 to both sides so that we now get the x all by itself. Whatever that is your answer. And that should be 2. 7. Add 2 to both. Well, you can do either or. I'm going to add the 4x over so that when we do that, not only does this cancel, make our 2 sides here, but that'll give me a positive x. It gives me a positive 2x. So this will give me a positive 2. I'm still going to have the 4 there. These have now canceled each other out. Set equal to a -10. Next step would be to subtract that 4 over. So that 2x would be a -14. Divide by 2. And our answer to that is -7. 8, 9, 10, and 11 deal with slope. There's a couple different ways we can do slope graphically. What is probably our preferred method is just by counting off the rise over the run. So you could really start at either one of these points. When we would have done these in class, I would label these as 1 and 2, and then I would typically ask somebody which one they want to start at. Doesn't matter which one we start at. I'm going to start at 1 in this case, so I'm going to go up 1, 2, 3. That's our rise. So initially, I probably would have written it with words. So I go up 3. Again, 1, 2, 3. And then my run, I'm going to go to the right. 1, 2, 3, 4. So I'm going to go right 4. We then assign positive and negative symbols to the up and the right. If I go up 3, that's a positive 3. If I go right 4, that's a positive 4. So this just becomes 3/4. The reason it doesn't matter which one you pick, let's say we would have picked this one instead and go to 2, we would go down 1, 2, 3. So now we would say we're going to go down 3. And then left 1, 2, 3, 4. Well, down 3 means -3. Left 4 means a -4. And then a -3 divided by -4 is a positive 3/4. So we get positive 3/4 either way. Nine, the same thought process. We're going to count off our rise over our run. I'm going to start with this point. Again, doesn't matter which one, but I'll start here. Go up 1, 2, 3, 4, 5, 6. And then go left 1, 2. So left 2. And then what we would understand is if I go up, that's a positive 6. If I go left, that's a negative 2. That then gives us a slope of negative 3. We've also talked if our line is going up, so this line is going up as we move from left to right, this slope has to be positive, which it was. This line is going downwards, therefore it better have been negative, which it is. When you're given 2 points, what we probably want to rely on is our slope formula. There's that. And what we would have talked about is you have 2 points. This is point number 1. This is point number 2. This notation right here, the y sub 2, means you're going to go to point number 2 and find the y coordinate in that point. So that's going to be 12. So I'm going to replace this y sub 2 with a 12. I'm going to replace the y sub 1. That's indicating we want to go to point number 1. And we want the y coordinate in point number 1. So that's going to be a 16. X sub 2 means you go to point number 2 and find the x coordinate in that point. So that's a negative 2. So we're going to plug a negative 2 in there. And then x sub 1 means you go to point number 1, do the x coordinate in that point, which is 7. So what we get on top is a negative 4. When we do a negative 2 and a negative 7, we get negative 9. While this is correct, your test will be multiple choice. And when we do multiple choice, we would never leave it written as a negative 4 over a negative 9. Negative divided by negative is positive. So we would just write this as a positive 4/9. All right, 11. The same thing. We just did the formula over here. Y2 minus Y1 over X2 minus X1. Second point, your y coordinate is this negative 11. So I'm going to replace that in right there. The first point, your y coordinate is a negative 15. X coordinate in point number 2 is this negative 7 right there. That's the second point, and that is this x coordinate. So I'll plug in a negative 7 into that spot. And then the x coordinate in the first point is the 8. So we're plugging in an 8 here. So pretty common to get these double negatives. So these end up being plus positive. We end up with 4 on top, negative 15 in our denominator. That's your answer. That's Module 1. That was just a review largely of everything you had done in Math 1, probably even dating back a little bit to 8th grade. We then went into Module 2. This is when we started getting into what we called quadratics. Quadratics are our parabolas, and in many ways, we dealt with those all semester. First thing we talked about is our vertex. So this is a nice one. This is what is in vertex form. If we remember, x plus a 14 means the point of our vertex, and the vertex is either the lowest point. In this instance over here, we also have parabolas that open downwards, and the vertex is your highest point. We can get that as long as it's in this form by looking at x plus a 14 and knowing that the x coordinate would be the opposite sign of that 14, so negative 14, and then our y coordinate, negative 8. That's vertex form. That's the only time we can look and identify right away what our vertex is. So in 13, notice how this is not in vertex form. This is what we would have called standard form. That's what we're looking at right now. And I want you to put this into vertex form. So we want to make it look like that one. So this is what we did over and over and over again. We've even done this in our last chapter when we were doing the square root method and perfect square method. We would draw this square out. The x squared would always get assigned to right here, and we knew that was always a result of doing x times x. The 6x, since it's going to be, again, a square, we want to split this perfectly, evenly, so that half go here and then half go here. So I have an x and a 3, x and a 3. So what we would then know is that this function can be rewritten as, see how we have an x plus a3 times an x plus a3. So we would write this as x plus 3, and then instead of doing it twice, we would just write it as the quantity squared. The constant is where we always had to make a little bit of an adjustment, because this constant that we get from x plus 3 times x plus 3 is a 9, but our original problem is a 14. So we said we could either figure out what do we need to do to 9 to get 14. In this case, we would subtract 5. So we've got to subtract 5 from this. I'm sorry, add 5. All right, 9 plus 5 will give you 14. Or we can take whatever this constant was, this 9, go up to the constant in the problem, this 14, and then always subtract it away from that. And 14 minus 9 gives you that 5. Now I can look at this. If this is in vertex form, we can write the vertex. While I didn't ask that question in 13, we can now find the vertex as negative 3, 5. 14 is the same as 13. We want to put this into vertex form so that I can look at the equation, identify the vertex. So this is where we want to create that perfect squared term. So the x squared here always goes upper left-hand corner. That's x times x. The negative 8x needs to get split evenly since we want to square here and here, so that we can now see that we have an x minus a 4 times an x minus a 4. So we really have x minus 4 squared. The constant that results from that in our perfect square, the negative 4 and the negative 4, would make a 16. But we wanted that to be a positive 3. So we can either just subtract the 16 from that to get negative 13. Or just understand if I want to go from 16 to 3, I would need to decrease 16 by 13. So we would do a minus a 13. This is our vertex form. This would allow us, if I asked, to identify our vertex by just looking at that as 4, negative 13. 15, when we want to graph this equation, the two big things that we can use to graph an equation are the vertex and the x-intercepts, if there are any. All right, so our vertex, we would want to put this into vertex form so that we know where to put that highest or lowest point that's going to be on our graph over here. So this now, we haven't done these recently when we started solving all these equations, but if you notice there's this 2 in front. So what we did with these 2x squareds when we did this to put this into vertex form, we would draw not just one square, because one squared would take care of an x squared, but since we had 2 of them, we would have actually have drawn out 2 of these squares. And then we would have had an x squared here as well. Sometimes we had 3. I gave you more than that, but we were pretty good back at that time, and we didn't necessarily need to draw all the pictures. We can kind of start to do this with some shortcuts. But that's what we would have started with, is like 2 and 3 and drawing them out. We would have then talked about, so we have the 2x squareds accounted for. We have 1 here and we have 1 here. The next thing we need to do is split up these negative 8s, but now that we have 2 of these squares over here, I need to put them equally in these 2 and these 2. So I'm really splitting it up equally 4 different ways. So if I had a negative 8 split up 4 different ways, we would do negative 2x all over the place, all right, in both of them. So what we would then see is that these are both x minus 2's. So when we go to put this in the vertex form, just like we did in 13 and 14 up here, you're going to go ahead and do y equals, and what we see is we have x minus 2 times x minus a 2. But notice how we have that again down here. So we have this twice. We have 2 of those, and that's why we drew 2 rectangles. Constant then that we're going to end up with down here, and then down here, we would have had a negative 2 times a negative 2, so 4 and 4. So overall, if we combine these 4, this 4 and this 4 give us a total of 8. So we go up here, subtract 8 from the constant of 6, and we should get negative 2. So this is vertex form. So I should now be able to ask what the vertex is. It would have to be a positive 2 and a negative 2. So plot that point, 2, negative 2. That's our vertex. The x-intercepts are what we just tested on. The x-intercepts are the same thing as your zeros, as your solutions, okay, all that fun stuff. And what we would do is we would take this equation and we would set it equal to a 0. And then what we would do is factor that and then solve it. So we haven't factored, we certainly have done a lot of trinomial factoring, but one of the things that we did back when we were doing all these and factoring a little more detail is we would always look at these values and see if there was a common factor. So if you look at 2, 8, and 6, those are all divisible by 2. And what we would do is pull out that common factor of 2. When I do that, the only thing left over for this first term would have been an x squared. And then I would have had minus, and I would ask 2 times what would have given us this 8, and that would have had to have been a 4. Then I'd have this plus sign, and then I would have asked 2 times what would have given us that 6, and that would have had to have been a 3. Once we pulled that 2 out, this is what we've been doing over and over and over again for the last month at least, is we want to factor this. And the two numbers that multiply to be a positive 3 and add up to be a negative 4 are a negative 3 and a negative 1. That's how those factor, or that factors with those factors. And then I would always ask, what makes this a solution? That would be 3. What makes this solution? That would be a positive 1. So these are your x-intercepts. So go to the x value of 1 on the x-axis. We're going to cross the x-axis there. Go to the x equals 3 on the x-axis, so here's 3. And then now we connect those guys with the vertex, and we have our parabola. Additionally, if you have your calculator, so while it's not necessarily what us as math teachers would want you to do, but it's a final and you want to do as well as you can, you have access to your calculator. So if there was a graphing calculator question or graphing a parabola question, there's nothing stopping us from just plugging this in. So if I go to my calculator and I plug in 2x squared minus 8x plus 6 and I hit graph, you can get your x and y intercepts by just looking at this 1 and 3. Your vertex is 2, negative 2, and then we can just sketch that in as long as we're hitting those points. Okay? So that's something that you might want to consider depending on how good you are, because this is a lot of work here. Whereas if you just put it into your calculator, it's kind of a okay way to cheat. Okay? All right. This here, when we would have done these, we would have talked about what is our vertex. That vertex point is a negative 2, positive 4. And we would then go to our equation. And what a lot of people did, even as we've been working through it Friday and this week, preparing for our final, a lot of people just wrote this and stopped. They understood that this was your x coordinate of the vertex. So we'd have x plus a 2 in the parentheses. Positive 4 means we're adding 4 on the end. But if you remember, again, it's been a while since we've done these. Remember how there was always that number out in front that would make sometimes our parabola more narrow? It could potentially make our parabola wider. It makes it open up and down. So there's this number here that we don't know. So we would still want to figure out, that was always the A. We would want to figure out what that point or what that value is. The way we did that is we looked at our parabola and we identified other points that the parabola went through. So it goes through this point, this point, this point, this point. You can use any of these other points that the graph goes through. I would probably use 0, 0, because zeros tend to make our work the easiest. This is an x coordinate. This is a y coordinate. So if you see the x is a 0, come over here to this x and let that x be a 0. At the same time, at that point, we see that our y coordinate is a 0. So go over to your y and let that be a 0. We just substitute in whatever point you would pick. I'm picking this one. We then simplify. So you're going to get 2 squared and then plus 4. 2 squared is a 4, so I really have 4a plus 4. Continue to solve this now for a. So we're going to subtract 4 from both sides so that we get a negative 4. These look like 9s equals 4a. Divide by 4, and what we find is our a is a negative 1. So we take that, go back in, and then now when we wrote this equation, we know there should have been a negative 1 in front. This is our complete equation. That should also make sense real quick because this parabola opened downwards, so we should have had a negative number in front of it. 17, another vertex form. So we're going to complete this square. X squared goes here, and we get that from x times x. The 12 x's get split equally between these two boxes, so 6 in one, 6 in the other. That means we have x plus 6, x plus 6. So when we go to write this in vertex form, we have 2x plus 6's, so that's what this means here, x plus 6 squared. The constant we get right here, though, in this square would be 36. We need it to be 32. So we just adjust by subtracting whatever constant we got here, the 36 from the 32. So we would need to decrease that by 4. That is vertex form. We now know if the question was asked, our vertex is -6, -4. (18) standard form. This is standard form. Okay. That's when we just have x squared, x to the first, and then your constant. That's what's called standard form. We want to put that in here. So this is kind of the opposite of what we've been doing in this review. What we did with these is we would have written this out, x plus 3 times x plus 3. All we're really doing is simplifying this. We want to multiply all that out, clean it up, add up our like terms. So I would ignore the 2 right now and then just deal with the x plus 3 times the x plus a 3. So I would do x times x. We're going to distribute. X times the 3. Sorry, x times x should have given us an x squared there. Then the 3 gets distributed. So 3 times x is 3x. 3 times 3 is 9. And then minus 22. Look inside of your parentheses. We have some like terms here that I'm going to combine first. So the 2 is still out in front. We have x squared now plus a 6x plus the 9, minus 22. Make some more space here. From this step, we're going to distribute the 2 now that this is completely simplified. So we're going to distribute the 2. So 2 times x squared. 2 times 6x. 2 times 9, 18. And then still got the little minus 22. Now we do end up with some like terms, final like terms here that we're going to be able to combine together. So f of x equals 2x squared plus 12x minus a 4. And then that's standard form. We have probably spent most of our time going from standard form into vertex form. This one was just asking us to start here and then instead work our way into standard form. But that was just cleaning everything up. 19. Did a bunch of these. Been a while, but a big part of that second chapter. This is in vertex form, so that's nice. Our vertex should be -4, -6. If you remember, so let me plot this point. -4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So this is going to be a parabola that opens downwards. And the reason let's go ahead and fill that in. The reason we know it opens down is because of this negative that's in front of the parentheses, that -2. Our axis of symmetry, I haven't talked about that in a while, is that line that cuts this parabola directly in half. So notice how it's a vertical line. The equation of any vertical line is always x set equal to some number. Well, the number that we have to be going through, if my vertex is a -4, -6, the x coordinate that I am going through has to be the x coordinate of this vertex. Okay, we can see it up here too, -1, -2, -3. This is a -4. So the axis of symmetry is a -4. If I look at my parabola, since this thing opens downwards and that's my vertex, this would have a high point on the graph. There's a maximum. The vertex is a max. And the maximum and minimum is always your y value. So the largest y value that this graph would ever hit would have to be this -6 right here. So we would say there's a maximum, and that maximum is the y value of -6. Your x-intercepts, there are none. Okay, since this is down here, opening downwards, there is no x-intercept. Your y-intercepts, if you look, this thing will eventually, if it comes down here, intercept the y-axis as we get really far down. So we just want to figure out what that is. So what we said, x-intercepts, the way we always found our x-intercepts, we just spent a whole chapter on this. Your x-intercept was always when your y value is a 0. So that's why we always set those equal to 0. Whenever we cross the y-axis, it's your x value that is equal to a 0. So what we would have done is we would have taken this equation here. So let me write that down here where we're finding the y-intercepts. And we want to know what happens when x is 0. So let your x be a 0. So if you notice, this was x. I just substituted in a 0 for that. And then now we clean this up. So this is 4 squared. Four squared is 16 minus a 6. Oops. Continue solving. -32 minus 6, which is a -38. So yeah, way down here to -38. All right, domain and range. The domain are all of your x's. So basically, how far left and right do we go? So every parabola that we did, and that's not going to change, this thing will go left and right forever. So -infinity to infinity. And then our range, this we would always talk about, does it go left and right forever? Your answer is yes. For the range, since it's your y values, we would ask, does it go up forever? That answer is no. Does it go down forever? That answer is a yes. So we definitely go down forever. And then the largest value that we would have hit, if we look at our vertex, if we look at this point, if we looked at what we would have talked about up here as our maximum y value would have been a -6. That would have to be our range. This is the biggest y value, and then we go all the way down to -infinity. All right, 20. Kind of the same process. We want to convert this into vertex form, and then we would want to graph this. So it's another one. If we're going to put this in vertex form, remember there's 2 x squareds. So this is when we would have done 2 of these boxes to make 2 perfect squares. So the x squared, one of them goes here, one of them goes here. That ensures that we get 2. The 20 x's have to get split equally. So highlight this. So these 20 x's get split now, not just between these 2, but we have another box of 2. So that I'm going to take those, split that equally 4 ways. So this would be 5, 5, 5, 5. So we now see we have x times, or x and a 5 across the top and the bottom for these. So we can go ahead and get this started. We have x plus 5 twice, but we have 2 of those. So we put the 2 out in front. The constant that we end up with combine here, so here and here, each one of them would have yielded a 25. So these 25s added up give us a total of 50 that I would subtract away from the constant in that problem of 47, so a -3. We now know our vertex is -5, -3. So 1, 2, 3, 4, 5, 1, 2, 3. All right, and then I want you to graph that. So now there's some different routes we could take here. You could try to solve this. So this would be the quadratic formula. I mean, you can certainly do that, but what we really did, and again, not everybody was able to do it because not all of you had a graphing calculator, but as these kind of got ugly, what I would tell you is just put this into the calculator. So 2x squared, and then this was plus 20x, and then what, plus 47. We would graph this. Notice this is our vertex. We said -5, -3 that we had, -5, -3. And then notice how these zeros were not nice. So we did one earlier in the review where it factored and we could find these x-intercepts nicely. So what I would suggest we do is go to your table. So here is that blue word table up here. Since it's blue and this is second function, I'm going to hit second table. And then we just write some points. So let's go to our vertex. Remember how we look at our vertex? Because -5, -3 is our vertex, we talk about how the number in front and behind, and then 2 in front and 2 behind would be the same. So we could graph it just based upon these ideas, okay? So if I were to now just write these handful of values in, so we would set up a table, and then do better. We're going to go -5, -3, and then we get the two numbers in front, the two numbers behind. We'd go to our table. All right. The -3 was surrounded by -1s. So we know each of these are -1s. And then 2 in front and 2 behind were 5 and 5. And then we plot those. So -6, 1, 2, 3, 4, 5, 6, -1, and then -4, -1. And then I'm going to plot these two guys, -7, 5, 1, 2, 3, 4, 5, and then -3, 5. That would be our graph. Again, it's going to be multiple choice. So if you know how to put this into the calculator, you really could just look at it and find the graph that looks like this. Okay, which one looks like the one that your calculator is showing you. Okay, it's not in here. Okay, 21. Similar question. It's not the same one, is it? Now that I look at it. No, it is not. Where we want to write this equation. So we'd identify this vertex. So this would be -2, 5. So because of that, we can definitely do the x plus 2 squared and then plus a 5. But again, we need to know what is that number in front that tells us how wide or narrow this graph is going to be, or if it opens up or it opens down, although in this case, we know that it opens down. So again, pick any point. This is a good point. This is a good point. That's a good point. That's a good point. I'm going to use this point right here. It has coordinates of 0, 1. Notice how this x coordinate, I'm going to just replace that in the x in the equation. That's going to be a 0, and then plus 2 quantity squared plus a 5. Y coordinate in that point is a 1, so I'm going to replace that y coordinate with a 1. And then now we have our a that I can solve for. So I'll do 1 equals, this would be 2 squared, and then plus 5. So I'm going to get a 4 times a plus 5. Subtract the 5 from both sides. And you're going to get 4a equals a -4. Divide by 4, and your a should be a -1. So now we can write this equation, replace it with -1, and then that's our equation for that parabola. Okay, 22. You're given the factored form. We want you to identify the vertex, x-intercepts, and then put it into the two different forms. So this is what we just did. X-intercepts are the same as your zeros. So what we would have done, we would have taken this, set it equal to a 0, and this is what I would have asked. When does this equal 0? That would have been 1. And then what number makes this factor equal to a 0? That would have been a -5. So we can plot that point, 1, and then the x-coordinate of -5. So those are our x-intercepts. Vertex, the way this is currently written, is hard to find. Okay. Again, I'll show you a cheat here. Let's go ahead and graph this, and then I'll show you how we can do it if you don't have the calculator. But we could just graph this as x minus 1 times x plus 5. So that's what our graph's going to look like. We can now find our vertex a couple different ways. Just look at the graph. This is a negative. Here's our vertex right here. The x-coordinate is a -2. The y-coordinate is 1, 2, 3, 4, 5, 6, 7, 8, 9. So -2, -9 is our vertex. Similar to what we did with our table in a previous question, if you saw the previous question, let's go to what we just said our vertex is, -2, -9. The other way we would know that this is our vertex, notice how the number in front and behind is the same. 2 in front, 2 behind are the same. 3 in front, 3 behind are the same. We know that's our vertex, -2, -9. If you don't, then you've got to go ahead and multiply all this out. So we're going to go ahead and do x times x, x times 5, a -1 times x, and then a -1 times 5, so -5. We have some like terms that we can combine right here. So when I multiply all that out, I get x squared plus 4x minus 5. This is our standard form. So this is going to go right here. When we multiply everything out, clean it all up, whatever results is our standard form. If we put it into vertex form, we already know we should get this, but this is, again, this is probably about the 6th time, 7th time I've done this on this review. If you've gotten this far, x squared is x times x. The 4x gets split equally here and here, so that we have x plus 2 times x plus 2. So I'll write that as x plus 2 squared. The constant that I get from this is a 4. So what I'm then going to do is come over here, and I'm going to subtract 4 from the constant that's in the problem, which is a -9. And then like this should, if we look at this, this should give us the same vertex that we found on our calculator. All right. Okay, 23. If I haven't told you in class, oh, no, that's not the one we're skipping. Sorry. Which one are we skipping? 24. All right, yeah. So 23, largely the same as what we just did. If I want my x-intercepts, your x-intercepts are your zeros, your solution. So we would have taken this expression and made our y-coordinate a 0. The answer that, or the number that makes that factor a 0 is 2. The x value that's going to make this factor a 0 is 8. So we're going to cross the x-axis at 2 and at 8. If you did not watch number 22 on the video, then I'll show you how we can do this again in somewhat cheat, but legally. I'm just going to graph this on the calculator. X minus 2, x minus 8. All right, then we hit graph. This is our vertex. So our vertex is right here at 1, 2, 3, 4, 5, and then down 1, 2, 3, 4, 5, 6, 7, 8, 9. So 5, -9. If you go to your table will also prove this. So if I go to 5, -9, notice how the point in front and the point behind are the same. And the point 2 in front, 2 behind, -5, -5, and then 0, 0, 7, 7. There's that symmetry around that point, so that guarantees that that's our vertex. Standard form is us just multiplying this guy out. So if I drop this down here and do x minus 2, x minus an 8, we just clean it up. So distribute x times x is x squared. X times a -8 is a -8x. -2 times x, and then a -2 times a -8 is 16. We end up with like terms right there, so that this gives you y equals x squared minus 10x plus 16. This is our standard form. Vertex form, again, done a ton of these in this review. We go ahead, set up our perfect square here. Here's x squared, that's an x and an x. The -10 we split equally here and here, so that we can now see we have x minus 5 times x minus 5. So I write that as x minus 5 squared. The constant that I get right here is 25. So then I'm going to subtract 25 from this, so that 16 minus 25 is a -9. And then again, this gives us this vertex. We can then, for the graph, plot this point, 5, -9. Connect those dots. I don't know if I did that in the previous question. And then that's our graph. Let me see. Yeah, I never finished this one off. So if I go plot the vertex here, -2, -9, and then I connect these, I missed. All right, that would be our graph. Okay, 24. Now this is the one that we're going to be skipping. All right, so there goes that. And we'll go down to here. All right, so 25. We want to solve that by completing the square. So again, another square. If we're good at anything in this review, it's probably what we've been doing the most so far. Make this a perfect square. So take the x squared, that goes here, and that's x times x. The -4x's get split equally because it's a square. And we see then that we have x minus 2, x minus a 2. The constant that we get from this is a 4, which is what we then subtract from this 5 right there. So what we would see is our function, oops, let me not do it that way, don't write f of x. All right, we have x minus 2 squared. And then when we get this 4, 5 minus that 4 is a positive 1. And then that's going to equal 0. What we would then do when we try to solve these is we would want to isolate this square term. So that would require us to subtract that 1 over. Cancels. And we would now get x minus 2 squared equals a -1. Pen's really being weird right now. Let me try this over here. All right, and then what that would then, once we have this isolated, this is when we started doing our square root. So we would do the square root of both sides. So x minus 2 squared divided by and then we're taking the square root of that. The square and the square root cancel, gives us x minus 2. We also have to do the square root on the right-hand side. Notice how we're taking the square root of a negative number. So a couple things here. Whenever we create our square root, there was always a positive and a negative answer to that. And then if you remember, the square root of a -1, that is the definition of I. So that's what we get there. It's an imaginary solution. It's one of these complex numbers in that number system. All right. From there, we add the 2 over. All right, let me try another pen real quick. Cancels there, and we add the 2. On the left-hand side, we just end up with that x now. And then what we get over here is the positive negative I increased by 2. All right, 26. This should just say use the quadratic formula to find the x-intercepts here. So quadratic formula, again, we're pretty good at these. This is somewhat recent, so hopefully we're pretty good with this. You need to know the quadratic formula, though. We need to remember how we find our A and our B and our C. So as long as this is in standard form, it's in the correct order. Your A in this case would have been the 2. The B in this case is a 3. And then your C would be the negative 5. All right, and then our quadratic formula is initially a negative B. Our B is a 3, so that means we would want a negative 3. And then quadratic formula, we would say plus or minus the big long square root of B squared, so 3 squared. And then we would always do minus 4, and then times A times C. A is the 2, C is the negative 5. And then all of that gets divided by twice A. A is a 2, so 2 times 2. All right, so negative 3 plus or minus 3 squared, which is a 9. Here's where we want to be most careful with our signs here. The initial 4 and negative 4 and 2 make a negative 8, but then that negative 8 multiplies by that negative 5 so that we get positive 40. And then all over a 4. So the negative 3 plus or minus square root of 49, all divided by 4. Square root of 49, 7 divided by 4. She'll have more room for this. And then we now go ahead and get these two answers. So one answer, I'm going to do the negative 3 plus 7 over 4. The other answer, I'm going to do a negative 3 minus 7 over 4. All right, so we get our two answers. So this is 4 divided by 4. So one answer is a 1. This would have been a negative 10 over a 4, which when we reduce that, reduces to be a negative 5 halves. Okay, this one would have just been 4 on top, 4 on the bottom, so that's why we get the 1. Okay, 27, finally a nice quick one. Solve by factoring. All right, the two numbers that multiply to be a negative 3, add up to be a negative 2, would be negative 3, positive 1. So my solution, one solution is 3. This other solution would be negative 1. All right, 28, another quadratic formula. Should be pretty good with these. So x would equal negative 3 plus or minus the b squared, so 3 squared minus 4 times 2 times negative 20. And then all over 2 times a. So we end up with negative 3 plus or minus. Let me move this over here. So negative 3 plus or minus 9. And again, be careful here. Negative 8 initially times a negative 20 is a positive 160. All over 2 times 2, which was 4. So this now gives us negative 3 plus or minus square root of 169 over a 4. Create a little space here. 169 is a nice perfect square of 13 divided by 4. So our two answers, one of them, I'm going to do a negative 13 minus 13 over 4. The other, I'm going to do a negative 13 plus 13 over 4. First answer, we get negative 16 divided by 4. So the negative 4 is one of our answers. And then this guy, negative 3 plus 13 is 10 over a 4. And then we can reduce 10 over 4 down to 5/2. All right. All right, 29, quadratic formula again. So you're going to do the opposite of b. So 2 plus or minus square root of a negative 2 squared minus 4 times 1 times 10. And then all of that gets divided by 2 times 1. Clean it all up. So 2 plus minus negative 2 squared is 4. And then now negative 4 times 1 is a negative 4. Negative 4 times 10 is a negative 40. And then 2 times 1 gives us this 2. I will get 2 plus or minus. Create some space, erase this previous one. Okay, that pen's a little tired, I hope. That's the problem. All right, so let me erase these. All right, and then we end up underneath with a negative 36, and then all over 2. So again, this is now what we just got done wrapping up. We're going to get 2 plus or minus, and then we had those negative radicals. We'd always do the number and then take the negative out with just a negative 1. So what this now gives us is 2 plus or minus. This is a nice 6. And then this root negative 1 is what I is. That's where the I comes from. So we now have 2 plus or minus 6I, all divided by 2. Each one of these guys here, we can reduce by a 2. So this 2 divided by 2 is a 1. This 6 divided by 2 is a 3. And then all over 2 divided by 2, which is a 1. So then this just ends up being our answer. Okay, so we definitely get some I's in those if you get a negative number underneath. Whew. All right. So for this quadratic formula, determine the nature of the x-intercept. So what we talked about with this, 2 big things. Were they real or imaginary? So the times when we get these I's, those are imaginary. When we don't get the I's, so like all these other problems before, all these answers to like 26, 27, and 28, those are real. And then we also wanted to be able to differentiate between rational and irrational. Irrational are when we get like root 3 that we can't simplify. Those are decimals that never end, okay? So that's what we want to identify here. So I would go about this, I think the best way, easiest way is using the quadratic formula. So 5 is your opposite of b. Negative 5 squared minus 4 times 2 times negative 3. And then all divided by 2 times a. All right, so we have our 5. You're going to do now 25 negative 4, right? The negative 4 and 2 make negative 8. A negative 8 times a negative 3, positive 24, all over 4. So this will give us 5 plus or minus. Again, erase some of this so I have room to work. 49, root 49. Divided by a 4, so then I get 5 plus or minus. Square root of 49 is 7. Divided by that 4. You can finish these if you want, but if we look at these are definitely two real solutions. We're not going to have any i's in it. And then if you look, we also get this nice, we talked about kind of what's underneath this radical here. This is a nice perfect square. So that's why it's going to be a real number. It's not negative. And then since this is a nice perfect square, this is going to give us our rational solution. So these are two real and rational solutions. Okay. All right, 35 or 31. I think the way this one sets up doesn't tell you which method to use. I think the square root method is the best, where we can just subtract this 25 over and get x squared equals a negative 25. We then get rid of the squared with the square roots. And then we end up with this negative radical. So again, we would split this into be 25 and then the negative 1. We should also, sorry, I forgot. Always give you guys a hard time. We should definitely get that plus minus. We get a positive and a negative solution. So we're going to get x equals positive and negative 5. That's the square root of 25. And then the square root of a negative 1 is I. So we have plus or minus 5i. Okay, 32 again. Types of solutions. Go quadratic formula. We're really just looking to kind of, what do we get underneath here? All right, is it a nice number, ugly number? Is it going to give us a negative radical to where we're going to get imaginary solutions? All right, so we'll plug that in. B squared is a 4 squared minus 4 times 3 times 2. That's our A, B, and then C, and then all divided by twice A. So we can kind of do this number out in front. We're certainly going to get a 6 in our denominator. But what we're really concerned about is what happens underneath the radical. So I'm going to get 16 minus, and then a negative 4 and 3 make a negative 12. And a negative 12 times 2 is a negative 24. So now in this one, notice how you are going to get a negative 8 under there. Okay. So again, you can finish this if you like. This one is not necessarily asking you. It's just asking what type of solutions do we get. And if you didn't watch the earlier one that was similar to this, what we want to compare is this real or imaginary. That's one of the big things we want to identify. And it would either be rational or irrational. Well, as soon as we start getting these negative numbers underneath, like we got up here in number 31, that's when we know we're dealing with an imaginary number. If we were to clean this up, we would get this to be 2i root 2 because of that negative underneath the radical. That's when we know it's imaginary. And because we end up with this root 2 here, it is also what we would say an irrational value. Okay, so that's sort of what we're getting at when we want to know the types of solutions. All right, 33. Nice one. Solve by factoring. So the numbers that multiply to be a negative 26 and add up to be 13 would be, or 11 would be 13 and negative 2. If you multiply these, you get negative 26. If you add these two guys, you get 11. So one solution that makes that a 0 is the negative 13. The solution that makes this a 0 would be a 2. All right, 34. 34, I is what root negative 1 is equivalent to. I squared is a 1. I'm sorry, negative 1. All right, that's the two big ones. Everything we largely did in this chapter was one of those two. A lot of times we end up with that root negative 1, so that's why some of our answers have i's. And then as long as we know I squared is a negative 1, we should be able to rewrite any of these with that idea. So if I have I cubed, this was I squared times I. I squared is in a negative 1, so I'm going to erase this I squared and know that this is a negative 1, but we have an extra I there, so negative 1i. I to the fourth is an I squared times an I squared, So it's really a -1 times a -1. So that's a +1. So those are the 4 different answers that we can get with these. Okay, we get a simple I, which is root -1, and we get -1, -1i, and then 1. Okay, 35. We are subtracting like terms. These are the ones where I always suggested, since there is a -1 right here, so that we keep our sign straight, I would distribute that. So the first quantity, not a lot's going to change. We'll just write this as 4 plus 7i. And then when we distribute, -1 times 3 is a -3. And then a -1 times a -5i is a +5i. Combine your like terms. So we have 4 and a -3, which is a 1. And then the other like terms are the 7i and the 5i for 12i. 36. Now we're multiplying. So we've done this a few times with non-imaginary numbers earlier in the review. You're going to do -3 times 2 is a -6. -3 times a -4 is a +12. And then with that I. Then I'm going to do 2i times 2, so 4i. And then a 2i times a -4i is a -8i squared. Make this a better 4. So -6, there is no other regular old negative, or no other constant number without that variable. But what you'll notice is we can go ahead and combine those two guys into be 16 i's. And then we also come across in this last term, this I squared here. And what we just said earlier is that that I squared is a -1. So we would want to replace I squared with a -1. So that what we end up with, -6 plus 16i, this ends up being a +8. And then now these guys do end up being like terms. So that should be 2 plus 16i. All right, last module. What we would want to do to graph this guy is just understand, if I ask you what kind of that vertex idea is, similar to a parabola, that since this is just an x, the x coordinate would be a 0, and then the 3 added on at the end is here. So this would be 0, 3, and then this would just be that v that opens upwards. Okay, since this number in front of the radical right here, it's just a +1, that's how we know it opens up. So if I ask you your domain and range, domain again is all of your x's. So if we look at this, how I always approach domain is I ask myself, does this go left forever? And you would say yes. And then does this go right forever? Which it does. There are no gaps anywhere. So our domain would just be -infinity to infinity. We hit every x value. Our range. Again, how I would always approach this, these are all of your y values, is I would ask you, does this go down forever? And we would say, no, this does not go down forever. And then I would say, does this go up forever? And it definitely does go up forever. So we're definitely going to a positive infinity. But what we would want to know is, what was the smallest y value that we would hit? So if we look at this graph right here, the smallest y value that we ever hit is, here's 1, 2, 3. That y value of 3 is our smallest y value. Okay, so we would go from 3 to infinity. All right, D, you did a bunch of these. The very first 4 questions on this review is you would take whatever function you were given, which is this guy right here. So I'll rewrite that down here. So f of x sorry, this is crapping out on me here. So your function is f of x equals the absolute value of x plus a 3. And then just like you did in the first 4 problems of this review, if x becomes a 1, so I'm going to erase this x, let that be a 1. That means I go to the other side of the equation and I plug in a 1 for that as well. And then we just do this. We evaluate it. So the absolute value of 1 is a 1, plus that 3, we have a functional value of 4. Whew. All right, 37. I want you to write the equation for the three lines shown to the right. So let's kind of highlight these. Sorry, it did not work. All right, so if I ask you to write the equation of this line, so let's call this line number 1 for now. All right. If it is a line, we know, hopefully know the equation of a line is always that y equals mx plus b, or the m is your slope. So if we look at this guy here, from this point to this point to this point to this point, we're going up to right 1, up to right 1, up to right 1. So we know the slope of that line to be a 2. The B is always your y-intercept. Well, while this doesn't hit the y-intercept yet, if we continued that pattern of up to right 1, up to right 1, up to right 1, notice where it would have hit the y-axis, and that would have been 1, 2, 3, 4, 5, 6. So that line would have had a y-intercept of 6. So that is the equation of that first line. All right. If I do that second line, so this will be our blue line. Couple different routes we could take here. You can still go with this whole little y equals mx plus b idea. It's certainly valid. And if I ask you to count off the slope, I'd go up 0, right 1, up 0, right 1, up 0, right 1. So what that tells us is the slope of this is really just a 0. And then this, we can definitely identify its y-intercept. This one very clearly crosses the y-axis at a positive 2. All right, that would work. I'd certainly accept that. But it's also this idea, if you remember, we talked about whenever you have a horizontal line, it is always y equals some number, and the y value is 2. That's the y value that we are going through. So that's really what happens here. 0 times x would just be a 0. So this would just go away, and all we get is the y to equal a 2. Okay, I'm going to write that now kind of normal, so that y is a 2. Okay, and then our third line, do this in purple, will be this guy. So my third line here, again, y equals mx plus b. The slope of this guy, we're going to go up 1, left 1, up 1, left 1, up 1, left 1, up 1, left 1. Or down 1, right 1, down 1, right 1. So the slope of that line should be a negative 1. And then we just need to know our y-intercept. So if we continue that pattern, up 1, left 1, up 1, left 1, up 1, left 1, up 1, left 1, that line, if it had continued, would have hit the y-axis at 3. Okay? So there's 3 different pieces to that function. Okay, so this is a function made up of 3 different pieces. It's just the equations of those 3 different lines. And then what you'll see is, this is something we'll kind of get into a little bit more as well. What we want to do is kind of define where these lines are actually defined at. So if we look at this yellow one, let me label this x-axis. So negative 1, negative 2, negative 3, negative 4, negative 5. The yellow one starts at negative 5 and stops at negative 2. So from a negative 5 to negative 2 is the first line. Notice how the blue one starts at negative 2 and stops at positive 1. So this one would go from a negative 2 to positive 1. So we just kind of put it in between those two in that inequality. And then the purple one starts at 1 and finishes at 1, 2, 3. So 1, 2, 3, 4, 5. So that one starts at 1, finishes at 5. All right. You will not have to write your own on the final. You're just going to see there's one that has a couple of them, and then you just want to be able to largely just identify what are those equations and be able to match it up. So you won't have to kind of put all of these guys together. Okay, then we get some domain questions. So this is old. Erase here. All right. Domain is, again, all the x values that we hit. And again, I always start with the domain by asking if we go left forever. We don't. And then I would ask, do we go right forever? And we don't. So what we would want to just understand, where do we start at? Like, what's our furthest left value? So negative 1, 2, 3, 4, 5. So this point starts at a negative 5. So that's the furthest left that we go. And the furthest right that we go is 1, 2, 3, 4, positive 5. So we just have all the values in between negative 5, positive 5. If I ask for your range, those are your y values. And same thing, do we go up forever in this graph? No. Does this graph go down forever? No. So what we just want to identify, what's the smallest y value is what we want to start at. So this is the lowest point on this graph. So if we look, this is negative 1, negative 2, negative 3, negative 4. So the lowest point on this graph is a negative 4. And the highest point on this graph is up here. And then that's at the y coordinate of 2, or y value of 2. So that's our range, smallest to largest y value. All right, and then we also did a bunch of function values just by looking at a graph. So if, again, this is normally f of x, what this means is when x equals a negative 2, what is your y value? So we come over here to a negative 2. Here is our graph. The y value when the x is a negative 2 right here is a positive 2. Okay, so that would be the point that's at x equals a negative 2. Okay, with these guys, these pieces here, the same thing that we did in the front page. So if we kind of go back all the way to those first 4 questions, that if I give you a function and I give you x values to plug in, we're going to take these x values, you're going to plug them into this function, and whatever that evaluates to be is your answer. Okay, so that's no different. What is a little different is this one has a few different functions. So let me pull it back up. All right, so the people who have asked about this, who have gotten to this, the way I kind of have explained this is if your x value is a negative 6, so again, f of x means my x value is a negative 6. I would ask you, does negative 6 fit in this window? Does it fit between 1 and 4? And for this one, we would say, no, that doesn't fit in there. So we're not going to use this function for this problem. Well, let's go up the next one. If I now ask you, does a negative 6 fit in between a negative 5 and a negative 1? You would again hopefully tell me, no, it does not fit in that window. If we go to the third and final one, if I ask you if a negative 6 fits somewhere between a negative 8 and a negative 5, now hopefully you would say, yeah, it does. So what we would want to do is use this function to find the value at a negative 6. And since the y value here is said to always be a negative 3, your function value is always a negative 3, that has to be f of negative 6. All right, must be negative 3. All right. So now in the next one, here's your x value. Your x is a 3. So now if I ask you, we'll go up again. Does 3 fit in this window there? And now hopefully you would say, yeah, it does. So what that means is we're going to plug x into this part of the function. So now in this here, you're going to do the negative 3 times x, so negative 3 times 3, and then plus that 6. So this would be negative 9 plus a 6. So now f of 3 would be negative 3. All right, next one. X is a 1. So same thought process. Does 1 fit here? This is the sneaky one. Letter C is the sneaky one because you have 2 different ones. So let's kind of make a note of that. We have a 1 here and you have a 1 right here. So we have to decide which one does it work in, okay? The first or the second one or the third one. So the answer to that, notice how this number 1 has an equal to sign and this one does not. So what that means is the 1 only fits into this one right here. It doesn't equal the 1. It's only greater than the 1, all right? So this is the one that we would use. So instead of x plus 2, you're going to let this x here be this x value of 1. So that f of 1, we would say, is 3. Okay, last one, f of 0. 0, if I ask you if it fits in here, you would hopefully say no. 0 does not fit between 1 and 4, so we want to use that one. If I ask you if 0 fits in between a -5 and 1, hopefully you would say, yeah, it does. So what that means is I'm using this function here to evaluate 0. So instead of x plus 2, that this is, you're going to replace that x with the x coordinate that you're told to replace it with, which is that 0. So f of 0 is a 2. All right, 39. These absolute value equations. If this is our original function, this is the one that we did our little table with and we graphed it, and I want this to go left 4 to the -4 and then up 9 so that now it's over here. Notice if my vertex is a -4, we would actually want to do x plus a 4 on the inside. And then if I'm going up here to the +9, I would add 9. So that's our new equation. All right, 40. Erase that. All right, we'll do this in pieces again. We have 2 different parts to this, 2 different pieces of this. We'll do this as yellow and blue. So the first one, the yellow one, again, just think of this as slope-intercept form. So y equals mx plus b, y equals mx plus b. All right, let's find the slope of this one. So this one were some good points. This is nice. So here, 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 here. So what we're really just doing is going up 1, left 1, 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 up 1, left 1. So the slope of this line is a -1. So we put that in front of the x. And then the b is your y-intercept. We can identify that very quickly. The y-intercept's a -3. So my first line has an equation of -1x minus a 3. All right, second one, the blue one. Same idea. Find your slope first. So I'm going to go up 1, right 2, up 1, right 2, up 1, right 2, up 1, right 2. So this has a slope of up 1, right 2. Our y-intercept, very simple. We go to the y-axis here. We would hit the y-axis at a +1. So the b becomes +1. So the second equation is y equals 1/2 x plus a 1. And again, you won't have to set all this up on the final, but then what this just kind of now gets in, since this is 2 different pieces, these are defined a little bit differently in terms of the domain, in terms of the x values. So if you notice, this one is only good for these negative x values, so -1, -2, -3. All right, all these negative x values over here. So this is only good for x values that are less than or equal to 0. The blue one, notice how it is graphed for all the positive x values. So it is good for when x is greater than 0. Excuse me. So those are our 2 equations, just again, slope-intercept form that we should be pretty comfortable with. And then it's just identifying, what x values does the graph exist for. All right, 41, similar to a previous one. If I ask you where does 5 fit, if the x value of 5, where is that going to fit? Again, it's f of x. The x has been replaced with a 5, so that means x is a 5. Well, 5 should fit right in here between 1 and a positive infinity. So what that means is I'm going to take this 5 and plug it into the x in this part of the function. Okay, so I'm going to do a negative 3 times 5 plus a 2. So that would be a negative 15 plus 2 for an answer of negative 13. All right, the next one. These are the ones that are a little sneakier. We did one of those on the previous one when there were different pieces to this. Negative 2, you'll see a negative 2 here. You're going to see a negative 2 there. So there's two of them that deal with the negative 2, but they can't use both. You have to pick one or the other. Since, see how this one doesn't have an equal sign under it and this one does? That's why we're going to use this one, because this is where the x truly equals the negative 2. So we're going to take this negative 2 and you're going to plug it into this part of this, or this part of the function. So x squared would become a negative 2 squared minus a 4, which is 4 minus a 4. So that answer is 0. All right, and the last one of these, we saw this. F of x became f of 1. So this is your x. So 1, if we look, fits right here because this is where the x is equal to a 1. So we're going to take that 1, plug it into this x value. So negative 3 times 1 plus 2 is a negative 3 plus 2. All right, we simplify. So that's going to be negative 1. All right, and then these. All right, been doing these, a couple of these every day here in the last week. All right, we want to isolate the absolute value bar, so we want to get this by itself. So the first thing we'd want to do is add that 9 over so that this would cancel. We now have a negative 5 times that absolute value 6x would equal a negative 60. We would then want to divide by the negative 5 to get that by itself. So what we would end up with is the absolute value of 6x is equal to 12, negative 60 divided by 5. This is now when we would set up our two different equations. We would take this 6x, set it equal to the positive 12, and we would take the 6x, set it equal to a negative 12. In both cases, we divide by 6. So in one instance, we get x to be a positive 2. And when we would divide this one by a 2, we would get x to be divide by 6. We would get to be a negative 2. Same process in 43. We want to get this by itself. So the first thing we want to do is add 8. Those will cancel, and we get 8, and then absolute value of n plus 3 equals a negative 72. Then we would want to divide by 8 so that this would go away. Divide the other side by 8, so now we get the absolute value of n plus a 3 is equal to a negative 9. This combo now is when we will get the answer of no solution. So we've done one of these every day for the last 3 days. The left-hand side here, sorry, clear that up. This left-hand side of the absolute value, this will always be positive. So there is no way it could ever be set equal to a negative number. This can never equal a negative 9. Okay, so that should be a no solution. All right, number 44. Here's our absolute value bars we want to get isolated. So the first step would be add 4. Cancels. We get 6. Absolute value of n minus a 2 equals 42. Divide by 6. So these will cancel. So we get the absolute value of n minus a 2 is equal to 7. And then there's two numbers that I could take the absolute value of here and get it to be a 7, both 7 and negative 7. So I'm going to take the m minus a 2, set it equal to 7, and I'm going to take m minus 2 and set it equal to a negative 7. Both of these equations you're going to add 2, giving you the solution of the first one to be a 9. When we add 2 to the second one, it gives us a second solution of negative 5. Last but not least, here's what we're trying to get by itself. So to start, we're going to subtract 4 from both sides. Cancels. So we now get that equal to 40, or I'm sorry, 70. We would then divide this 10 over. Cancels, and we get negative 2 plus r equals 7. And now we get our two different equations. We want to know what would make this a positive 7 and negative 7, so that the absolute value would be a 7. So we take the negative 2 plus r equals 7, and we do the negative 2 plus r equals a negative 7. Add 2. One answer is a 9. Add 2 here. Second solution, negative 5.